And now, please welcome to the stage, Nicholas Kokoulekidis.
So I would just like to invite Robert Koenig, the Program Committee Chair, and Angela Capel, the Program Committee Co-Chair, to perform the award ceremony for the best student papers of the year.
Okay, it's my pleasure to announce that, as you know, we have the Best Student Paper Award, and this year it was given to 4 students. And we thought it's more appropriate if the awardees are introduced by someone who pioneered the field. So we have here the C of CSS codes, Robert Calderbank. So,
all right. So, thank you very much for that very generous and very brief introduction. It is a great pleasure for me to see that quantum error correction is still very much alive and kicking. And it is my great pleasure to introduce the winners of the student awards. So we have 4, and the first is Adam Wills for advances in transversal non-Clifford Gates and Magic State Distillation. And Louis Golowich, same. And Quynh Nguyen. Same paper. And finally, David Lin. You're in charge.
okay, thank you very much. So with this, I'd like to hand over. You have a lot to tell us. So,
So Adam Wills will kick off the session.
Great. Thanks very much for that introduction, and thank you all for coming. So we're going to talk about these advances in quantum coding theory and the applications to magic state distillation. This is a merge of 4 papers, as was mentioned. So just as a bit of a roadmap, the first 3 papers do pretty similar things with quite similar methods, and so they'll kind of be mashed together. And the 4th paper of Louis and David's is closely related, but does something a bit different, as we'll describe. So for my part, I'm just going to be covering the overview and the big concepts, their definitions and motivations, and give the big results, that kind of thing. So the core concept is a transversal gate, so we'll start with that. What we want to do is compute on the information contained in a quantum code, and we want to do that fault-tolerantly. Okay? And so one of the best ways to do that fault-tolerantly is to do it via a low-depth circuit on the physical qubits. But this isn't something that you expect to be able to do all the time. So as a concrete example, we'll be considering the CCZ gate a lot. And so imagine that you have this code, and it has this nice property that you can take 3 code blocks, stack them on top of each other, and you can execute a physical CCZ across the physical qubits. And it has the effect of executing logical CCZ across the logical qubits. You would say this code supports a transversal CCZ gate. And the point is that this is an inherently fault-tolerant way to do quantum computation on the encoded information, because errors can't spread within a code block. I'd also point out that it's an inherently low overhead way to do fault-tolerant quantum computation, because there's very little in the way of space-time overhead beyond just the code itself. And so if we could do just transversal gates, we probably would. The trouble is that there's this very well-known no-go theorem called the Easton-Nil theorem, and it says there cannot be a code supporting a universal set of transversal gates. We need to do something else. And that something else is often taken to be magic state distillation. So we'll be working in this very common setup where we do all the Clifford gates transversally, and then we do a non-Clifford gate with magic state distillation, and that gives us everything we need. So I'll say what magic state distillation is, and to do that, I should say what magic states are. So a magic state is essentially an encoding of a gate into a state, especially a non-Clifford gate. Okay? And most commonly, it's that gate acting on a bunch of copies of plus. So again, to be concrete, the one we care about most will be the CCZ state. And this will just be the CCZ gate acting on plus, plus, plus. And as I claim, this is really an encoding of the gate in the state. And so up to normalization, you can see the entries of the CCZ gate, which are just 1, 1, 1, 1, 1, 1, 1, minus 1. And the reason we care about these magic states is because we can sort of think of them as being equivalent to the gate itself. So, of course, if you can do the gate, you can make the state by just acting on the pluses. But it goes the other way, too. So if you have the state, then you can run this gate teleportation circuit, and you can execute the gate on some other state, possibly even a state that's unknown to you. And fortunately, this gate teleportation circuit runs via Cliffords only. And so in our setup, where we're doing Clifford gates transversally, and we're doing the non-Clifford with magic state distillation, the Cliffords are deemed to be kind of the cheap operations. So this gate teleportation is deemed to be quite cheap, so we can kind of think of the gate and the state as being equivalent resources. So we've reduced the problem of doing a non-Clifford gate down to getting the magic states. Magic state distillation is then going to solve the problem for us of making these high-quality magic states. So we can make low-quality magic states in the lab, but what magic state distillation is going to do for us is going to allow us to take in a large number of low-quality or high-noise magic states and turn them into a smaller number of high-quality or low-noise or low-error rate magic states. And this will run via Cliffords only, so we're in business. The trouble is that magic state distillation is very expensive. We would like to do it more efficiently if we can, and more efficiently means doing it with a lower overhead. So I'll say now what the meaning of overhead is in this talk. So consider this kind of just pictorial representation of MSD. So you're just taking in some large number n of magic states, in our case, the CCZ state. We do some magic state distillation, and we get out some smaller number k of less noisy magic states. And suppose the input error rate is just some constant. The constant doesn't really matter as long as it's below a threshold. And suppose the output error rate is some epsilon. Then for us, the overhead is going to be nothing more than n over k, the ratio of the number of inputs to outputs. But I do want to mention that in other contexts, especially more practical contexts, you might think more about the space-time cost of implementing the MSD. But for us, and this is quite a theoretical thing to do, we're just going to say the overhead is magic states in versus magic states out. So the overhead is really a function of epsilon as epsilon's getting small. And its functional form is always going to be polylogarithmic in 1 over epsilon. So the thing that we want to control, the thing that we want to suppress to make the overhead smaller, is the degree of this polylogarithm. And this degree is very commonly written as gamma and is known as the overhead exponent, or sometimes the yield parameter of magic state distillation. So this gives me enough to state the main results of the works. And the first of these is that we can get gamma equals 0 for qubits. And while qubits is the main case of interest, this is really achievable for any qubit of your choice. I should compare this to the previous state of the art just for the sake of some context. So the previously lowest known value of gamma for qubits was 0.678 due to Hastings and Hsieh, and this was found in 2017. But in the following year, Krishna and Tillis showed that you could do much better if you just allowed yourself to use larger qubits. So they showed a family of protocols where if you go into the limit of the family, then you can suppress gamma down to 0, but it was at the cost of a diverging qubit dimension. So it was open previous to the present works, whether you could get small gamma for a fixed qubit. So result 2 is the main reason we're able to get result 1. This is the construction of the first asymptotically good quantum codes to support non-Clifford transversal gates. And we're able to get nice gates like the CCZ gate to be transversal. We're also able to get these codes to be explicit. That just means that we can write them down in a reasonable amount of time. One of the problems with the constructions in result 2 is that they're not LDPC. They don't have constant weight stabilizers. They're actually maximally not LDPC. They have massive linear weight stabilizers. And so it's very natural to ask, what is the best you can do for an LDPC code with a non-Clifford transversal gate like CCZ? And so this is what Louis and David's paper is doing, the 4th paper, which we'll hear more about at the end. So this is result 3 from their paper, which is a near LDPC code in the sense that it has polylogarithmic stabilizer weight, supports non-Clifford transversal gates. Again, they can get nice gates like CCZ. And instead of being asymptotically good, they have distance n to the 3rd and almost linear dimension. But this was the first time that people have got polynomials here for this problem, so it's a big step forward. And again, they can get these codes to be explicit. So the plan is for the others to tell you more about the code constructions. I've kind of got the easy job. I just want to draw the connection between codes and magic state distillation. So why, if you construct a quantum code supporting a non-Clifford transversal gate, should you expect to be able to make a magic state distillation protocol for the corresponding state? And why, if you improve the error correction parameters on that code, would you expect to be able to do more efficient MSD? Well, this connection was first formally drawn by Bravi and Hsieh in 2012. And they showed that if you have a quantum code supporting a non-Clifford transversal gate, and it has parameters nkd, meaning it has n physical qubits, k logical qubits, and distance d, then you can get distillation for the corresponding state with gamma is log n over k over log d. So as I claim, if you improve the error correction parameters, that is, you get more logical qubits k, higher distance d with respect to the number of physical qubits n, you will be able to suppress a gamma here. Clearly, at the same time, you're not going to be able to get this constant overhead with this formula. So this requires us to go beyond this, this routine. And so what I'll show you now is how you would do distillation with constant overhead given an asymptotically good code. So what we start by doing is we take k copies of the plus state times 3, and we encode them all into the code. Notice that this is all going to be a Clifford circuit, and in particular, encoding into a stabilizer code is always Clifford. So at this point, we have 3 code blocks stacked on top of each other, and they're all filled up with pluses. What we now do is we take in the input noisy magic states, and we're distilling CCZ, so this is n noisy CCZ states. And we run the gate teleportation circuit, and this has the effect of executing transversal CCZ across the physical qubits, like I described earlier. And because our code supports a transversal CCZ gate, this has the effect of executing the logical CCZ across the logical qubits. Then, of course, the CCZ state is nothing more than the CCZ gate acting on plus, plus, plus. And so what we get here is k copies of the CCZ state. The problem, of course, is that there was some noise on these inputted magic states, so there's some noise in the gate teleportation operations, so there's some noise on this state here. But the point is, we're in a code, and so we can try and get rid of some of this noise, or at least discretize it by measuring the stabilizers. And this kind of snaps us into one of the syndrome spaces. We can then extract that syndrome, and we can do a decoding operation, which we show can be done classically and efficiently. And from that, you can determine what recovery operation do I perform to try and correct the effect of this noise. We do that error correction. You can show that most of the time that pulls you back into the code space where you want to be. And the analysis shows that the asymptotic goodness of the code proves constant overhead and constant threshold distillation for the CCZ state. And with that, I'll hand over to Quynh to say more about the code constructions.
Hello. Hi, everyone. Yeah, so thanks, Adam, for introducing transversal gates and constant overhead MSD. So I will now tell you about our construction of the first asymptotically good quantum codes with a transversal non-Clifford gate. And in particular, in this talk, we focus on the CCZ gate. So our construction is quite modular. It has 3 components. I will tell you about the first 2, and Louis will tell you about the 3rd component. So just as an overview, so in the first step, we'll construct a quantum CSS code from a classical code satisfying the so-called multiplication property. And we'll show that this quantum CSS code has a transversal CCC gate. In the second step, we'll instantiate this classical code, and it will turn out that the classical codes with this property that are available for us are only known on qubit of a dimension larger than 2. And this requires us to do the qubit to qubit conversion in step 3. Okay, so because we'll work with qubits, let me just give a quick reminder of qubits and CSS codes over finite fields. So we'll work with finite fields of size q, and in this talk, we'll take q to be a power of 2, but all the results are readily generalized to any prime power. Okay. So we can define a qubit over this finite field. So the computational basis states are labeled by the field elements. If you're not familiar with finite fields, it suffices for the rest of the talk to know that you can do the usual algebra on finite fields. You can define the qubit versions of the polygroups, etc. And a good reference for this is this textbook. That's a special function over finite fields called the trace map, which is a linear map mapping from FQ to the base field F2. I won't tell you the exact definition of this trace map, but it's all you need to know is that it's linear. So with this trace map, you can define a qubit version of the CCC gate, and it applies a -1 phase whenever the trace of the product of x, y, z is equal to 1. So from this definition, it's easy to see that when q is equal to 2, we recover our familiar CCC gate for qubits. Okay. And you can also define the qubit versions of CSS codes, and the definition is exactly similar to the qubit case. So given two classical linear codes, C1 and C2, such that C2 is a subset of C1, the quantum code is the span of the code set states. Okay, so what is the multiplication property? So this is a property of classical codes, and it's, I guess, more well-known in our quantum coding theory as the tri-orthogonality condition. So this condition reads that any 3 code words of the code must have a triple dot product equals 0. And the triple dot product is defined in this expression. So alternatively, we can denote this condition in this shorthand notation, which say that C star C is a subset of the dual code. And the reason for this notation is because from this condition, you can see that it's asking that the bitwise product of any code words x and y is orthogonal to any code word z. That means the bitwise product of x and y is in the dual code. So the main lemma behind our construction is the following. Given a classical linear code C with this multiplication property, we can construct a quantum code such that the depth 1 transversal applications of the CCZ gates realizes the logical CCZ gate on all the logical qubits. And furthermore, if the classical code and its dual are both asymptotically good, then so is the quantum code. A version of this lemma has already appeared in a beautiful work by Krishna and Tillage from 2018, and essentially what we did here is a direct generalization of this to the case of prime power finite fields and multi-qubit gates. Okay, so I will now tell you a sketch of the proof of this lemma. So first, let's see how the quantum code is constructed. So we will start by expressing the generating matrix G of the classical code in this systematic form. So in particular, in the top left block of the matrix, we'll have the identity matrix of dimension k by k, where k here is some number that we'll choose, and k has to be smaller than k primed. And as a reminder, the classical code parameters are primed in this lemma. So n prime, k prime, d prime are the code parameters of C. So the quantum CSS code we'll have k logical qubits, and the number of physical qubits is n prime minus k. And in particular, the C1 in the CSS construction will be the row span of the matrices H1 and H0 on the right-hand side, and C2 is the row span of H0. So with some work, you can show that the quantum code parameters are indeed asymptotically good when C and C perp are good. But the more interesting property that is relevant to us today is this second property, which follows from the multiplication property. And it says that any 3 rows in this matrix H1, H0 has a triple dot product being 0, except when the 3 rows are the same and they belong to H1. And now I'll show you why this claim number 2 implies that the CC gate is transversal. And the intuition here is just because CCZ gate is a multiplication, a triple multiplication in the computational basis. And this claim number 2 will allow us to convert this physical multiplication into the logical space. So let's analyze the action of CCZ tensor N on these 3 code words, UVW. So each CCZ gate will give you a phase determined by the triple product of the physical qubits at location I. And then you multiply the phases together. But we can use the linearity of the trace map to bring this product up to the exponent inside the trace. And now we have this sum. And now what we do is we simplify the sum. And claim number 2 allows us to show that this sum is independent of the H, H prime, and H double prime. In other words, this sum is only dependent on which coset the bit string is in. And with some math, you can show that this sum is equal to exactly the triple dot product of the logical qubits. And that's exactly the logical CCZ gate. OK, so that concludes the first step. So now, in the second step, we'll instantiate this construction with a classical code with multiplication property. So there's a very well-known code family with this property called Reed-Solomon codes. So these codes are evaluations of low-degree polynomials on a finite field. So more precisely, a Reed-Solomon code of parameter q and k is the evaluations of polynomials of degree at most degree less than k over fq. So the parameters of these codes are given in this formula, and there are 2 interesting facts about this code. One is that the star product of a Reed-Solomon code of degree k with itself is contained in the Reed-Solomon code of degree 2k minus 1. This fact is very intuitive because this star product is equivalent to multiplying 2 polynomials of degree less than k. So you can get at most a polynomial of degree at 2k minus 2. The second fact is less trivial. It says that the dual of a Reed-Solomon code of degree k is a Reed-Solomon code of degree q minus k plus 1. So from these 2 facts, we can see that when k is less than q over 3, then we have the multiplication property. And so we can plug this code into the classical to quantum code construction and get a code with transversal CCZ gate over a qubit dimension q. The issue with this construction is that the code size is limited by the alphabet size. In particular, n is at most q in this construction. And this is the same issue encountered in the paper of Krishna and Tillich. So we'll resolve this issue by considering a fancier version of Reed-Solomon codes called algebraic geometry, or AG codes. So describing this AG code construction is a bit complicated for this talk. So instead, I'll try to give an intuition why this code could improve the Reed-Solomon codes over the Reed-Solomon codes. In fact, I'll start with another natural attempt, which is to use Reed-Muller codes. So this Reed-Muller codes is a multivariate version of Reed-Solomon codes. So in particular, they are evaluations of multivariate polynomials over all the points in the hypercube of t dimensions. And t here is the number of variables. So this multivariateness of this code allows us to get a growing code family by growing t, the number of variables, while keeping the alphabet constant sized. So this is great. Now we have a code family with growing size, with constant alphabet. The issue with this code is that we cannot get an asymptotically good parameters over constant sized alphabet. And this is the same issue also that was run into in also a previous work in Magic State Distillation by Hsieh and Hsieh. So the magical thing is that this algebraic geometry codes can resolve this. And the idea of this is that instead of evaluating these multivariate polynomials on the entire hypercube, we can instead pick a very nice collection of points inside this hypercube in order to minimize the number of physical qubits while roughly maintaining the other code parameters. And the choice being made in AG codes is that this collection of points can be specified by an algebraic curve. And with some sophisticated construction of this algebraic curve can give you the code family that we want. In particular, we can have some appropriate modifications of some of the code family in existing literature by Stishanov to get an AG code family, asymptotically good family, with the desired properties for our quantum code construction with only a constant sized alphabet of size, for example, 64. So then this allows us to get an F64 quantum code with transversal CCZ gate. So this concludes the second step in the construction, and now Louis will tell you how to perform the alphabet reduction to get a qubit code.
Thanks, Quynh. Great. So just to recap, as Quynh described, our goal is to get a qubit code, a binary code with transversal CCZ gates. And so far, we've seen how to get a qdit code, where q is the power of 2, with transversal CCZ gates over fq. And so the solution, the way we'll go from this qdit code to this qubit code, is to concatenate the qdit code with what's called a multiplication-friendly encoding. And this is basically a way of encoding elements of fq such that we can perform multiplication over fq. We can compute this product, x times y times z, in the definition of the CCZ-q gate using multiplication over f2, which occurs in the definition of the CCZ-2 gate. Great. So what is a multiplication-friendly encoding? At a technical level, it's a set of 4 functions, 3 encoding functions and 1 decoding function, with the following property. If we have any 3 elements of fq, z1 through z3, and then we encode these 3 elements into 3 bit strings of length b over f2, we want it to be so that if we perform transversal multiplication on these 3 bit strings, so we get a product bit string, again of length b, and we decode, we apply the decoding function to this product bit string, we want to recover the product z1 times z2 times z3. This is the product over fq. So essentially, this multiplication-friendly encoding is letting us compute products over fq by performing transversal multiplication over f2. Now, it turns out that these multiplication-friendly encodings always exist. For any q that's a power of 2, there exists a multiplication-friendly encoding. And there's a couple of different ways to construct them. Maybe the simplest, though not the construction achieving the best asymptotic parameters, but for the purpose of this talk, it's OK to just basically use a repetition code. We can basically just define each of the encoding functions to repeat each input bit m squared times, and then permute the resulting m cubed bits in an appropriate manner. At a high level, this works because multiplication over fq is actually a multilinear function over f2. And what that means is that if we take our 3 inputs, z1, z2, and z3 in fq, we can write each one of them as a length m bit string over f2, and then we can compute the product over fq by just computing products of these bits over f2 and adding them together in an appropriate manner. And at a high level, this repetition code encoding that we want to use essentially ensures that we can perform all of these products over F2 using kind of different copies of our repeated bits without ever reusing a bit. So we can really get this transversal multiplication structure that we saw in the previous slide in the definition of a multiplication-friendly encoding. So that was maybe a bit of quick intuition. It turns out that you can formalize this intuition fairly directly and get these multiplication-friendly encodings. And then we arrive at our theorem, which is a family of asymptotically good binary quantum codes with transversal CCZ. And we've basically already alluded to how we're going to prove this result. We basically start with our asymptotically good QDIT code that Quynh described based on like the algebraic geometry codes that has a transversal CCZ Q gate. And then we concatenate this code, so 3 copies of this code, with the 3 respective encoding maps from our multiplication-friendly encoding. So if we start with a length n QDIT code, we encode each of these QDITs into b qubits using our multiplication-friendly encoding, and we get a length n times b qubit code. But here b will be a constant, because as Quynh described, these QDIT codes have constant q. So it's just we get a constant factor blowup in the parameters of our asymptotically good code, so it's still asymptotically good. And we now actually have a transversal CCZ gate over F2. And the intuition here is that the physical gate we'll apply consists of binary CCZ gates on triples of qubits across the 3 codes, where the precise triples of qubits that we apply a CCZ to is determined by actually the multiplication-friendly decoding map. Essentially, this decoding map is allowing us to compute the product over FQ, or the CCZ Q gate, and simulate this gate using just products over F2, or using CCZ2 gates. Great. So this is our main result on asymptotically good binary CCZ codes. I'm now going to transition a bit and actually talk about one downside of these codes, one disadvantage that Adam mentioned at the start of the talk, which is that these codes actually have large stabilizer weight. So we can briefly recall that a code of stabilizer weight W is a quantum code that permits error correction using what's called stabilizer measurements, each of which touches W qubits. And visually, what that looks like is if we have some corrupted code state, so say in this example, 3 errors have occurred, we can perform, or at least the standard way of doing error correction on stabilizer codes is to perform these stabilizer measurements, where we just measure tensor products of Pauli operators, called stabilizers. So we might measure like the tensor product of Pauli x's on these 3 qubits, the tensor product of Pauli x's on these 3 qubits, some Pauli z's, and a lot more of these Pauli operators. And we take all of these stabilizer measurements, we combine them, we perform some post-processing, and hopefully we can use the measurement outcomes to infer and then correct whatever error occurred. Now, if all of these stabilizers have weight at most W, so they all touch at most W qubits in the code, we say our code has stabilizer weight W. And unfortunately, our asymptotically good codes actually have linearly large stabilizer weight. The stabilizer weight grows linearly in the block length. And this is not ideal for a couple reasons. For one, in order to measure a linear weight stabilizer, you need to perform an operation that touches all of the qubits, which means that you could actually potentially corrupt any of the qubits, or all of the qubits. So performing this high-weight stabilizer measurement will not be inherently fault-tolerant. We'll need maybe some sort of concatenation with another code that actually can correct errors in a more fault-tolerant manner to achieve a fault-tolerant protocol. And this is why a lot of these magic state distillation schemes, even the ones that Adam described at the start of the talk, typically involve some sort of concatenation with something like a surface code. But even then, even for magic state distillation, these high-weight stabilizer measurements in a concatenated scheme will be fault-tolerant, but they'll still be inefficient because it'll just take a lot of time or space to measure all of these high-weight stabilizers. So really, this is saying that the ideal object to do these CCZ gates or magic state distillation in an efficient manner would be a good quantum LDPC code. That is a quantum code with stabilizer weight, with constant stabilizer weight, that has a transversal CCZ gate. And these codes would permit more efficient fault-tolerant error correction without any concatenation. They would reduce the space-time overhead of magic state distillation as well. Great. So we don't get all the way there to asymptotically good quantum codes with transversal CCZ gates, but we do get some significant improvements on the prior state of the art. So specifically, I guess the final main result we'll present in this talk is a construction of quantum codes with transversal CCZ gates that have polylogarithmic stabilizer weight, so they're like, I guess, nearly LDPC. And they have dimension growing almost linearly in the block length, so dimension n to the 1 minus epsilon for a length n code, and distance roughly n to the 1/3. And we want to emphasize that these codes really support transversal CCZ in a very strong sense. We're saying that you can perform physical CCZs on disjoint triples of qubits, so there's no error propagation within blocks when you perform these gates. And that induces the action of logical CCZs on k disjoint triples of logical qubits. And the disjointness on the logical side means that you don't have unwanted entanglement arising between your logical qubits. So for instance, if you're going to perform magic state distillation using these codes, you'll get k totally unentangled true magic CCZ states, which is what we'd want out of distillation. So to the best of our knowledge, these are the only known codes with low-weight stabilizers and with the magic state yield parameter gamma becoming arbitrarily small. The prior state-of-the-art construction was the 3D toric or surface or color code. They're all roughly similar to each other, and they all obtain these parameters where a length n code encodes a constant number of logical qubits at a distance roughly n to the 1/3 with constant stabilizer weight. So you can see that our codes of almost linear dimension kind of improve the number of logical qubits from just constant to almost linear, which is, I guess, a pretty substantial improvement, though at the cost of a polylogarithmic loss in the other parameters. There was some additional prior work in the low distance regime, like the logarithmic or polylogarithmic distance regime. And also, after our work, Guan had a very nice follow-up that constructed these very nice quantum LDPC codes with transversal CCZ that beat the color code parameters, though don't quite achieve gamma going to 0. Great. So at a high level, our proof is to take classical Reed-Muller codes, which Quynh described earlier. They're actually a family of classical LDPC codes with a multiplication property, and map them to quantum LDPC codes with a transversal CCZ gate. Now you may kind of think, oh, this is kind of another instance of what we saw earlier. Kind of, we're probably just going to say, again, take this multiplication property, map it directly to a CCZ gate. We saw it work for the asymptotically good codes. It'll probably work here as well. At a very high level, this is what we do, though it turns out that in the LDPC setting, there's a number of additional details, and we actually need to do a lot more work to get this transformation to work out. At a high level, this transformation will now involve two steps, both of which are somewhat different from the non-LDPC setting. The first step is actually to take these Reed-Muller codes and embed them into a new family of classical LDPC codes based on some new expander graphs. So somehow, unlike with kind of Reed-Solomon or AG codes, where we could directly map them into a CSS construction, to get good quantum LDPC codes from Reed-Muller codes, we need to first kind of transform the Reed-Muller code. As I'll describe in a bit, we need to essentially sparsify it, and only then can we get a reasonable quantum LDPC code out of it. And even once we have, once we have this quantum LDPC code, which ultimately will come from a 3-dimensional hypergraph product of these sparsified Reed-Muller codes, it's then another challenge to actually show that these quantum LDPC codes have transversal CCZ gates. And David will give more details on this later, but it actually requires some additional ideas from algebraic topology using something called a cup product. So before passing it off to David, I'll just give a few more details on the first of these two steps, kind of embedding these Reed-Muller codes into some new LDPC codes. And just to recap, as Quynh mentioned before, Reed-Solomon codes are these non-LDPC classical codes with a multiplication property based on univariate polynomials, while Reed-Muller codes are the multivariate LDPC versions or analogs of Reed-Solomon codes. So what that means at a visual level is that the code components of a Reed-Muller code correspond to points in a high-dimensional vector space, fq to the t. Here you can think of t as growing like polynomially in q. And the low-weight checks, or the classical analog of our stabilizer measurements, for Reed-Muller codes will correspond to essentially Reed-Solomon codes along lines through this high-dimensional vector space. And since each line through this vector space has length q, and here q is much smaller than the code length, which is q to the t, these codes do have low-weight checks. They are LDPC or nearly LDPC. And it turns out that there's actually so many lines through a high-dimensional vector space that we actually can't immediately get a good quantum code out of these codes. Essentially because each code component of our classical code kind of has like a linear number of lines or like an almost linear number of checks passing through it. And so if you then try to take a hypergraph product of these classical codes with so many parity checks, you actually get a quantum code that is poor stabilizer weight and poor distance. So we resolve this problem in essentially maybe it's the most natural manner. We just sparsify these checks. We subsample down to just choose like 2 specific lines passing through each point. Just taking a very small fraction of all the checks in the Reed-Muller code. And by choosing these lines according to an expander graph, we're able to show that the resulting sparsified code still is good distance. Great. So that's all I'm going to say about this step. And I'll now pass it off to David to talk about the final step in our construction, which is to lift this local multiplication property in the Reed-Muller code to a transversal CCZ gate. I'm using some topological techniques.
Okay. All right. Hi. So yeah, thanks, Louis. And before continuing, let me just recap. So our goal is to build codes with transversal CCZ gates. And to do so, we try to satisfy this multiplication property, or as I later call it, the triorthogonal condition. And so it's really this expression, which is like you take 3-bit strings, and you have to satisfy that this expression. OK. So from the previous part, we learned an algebraic method to satisfy these conditions, in particular using Reed-Solomon code and algebraic geometry codes. For this part, we'll learn a different strategy using topological method, and which uses this triple intersection and cup product. Okay. And as a side note, this triple intersection and cup product, they're really the same thing. They're related by this thing known as Poincare duality. So for the later parts, we'll mainly use the language of triple intersection. But if you see some paper that mentions cup products, it's really the same thing. OK. So all right, so let's start. So to motivate this notion of triple intersection, let me just briefly review some of the codes that is known to have these non-Clifford gates. So one of the code with this non-Clifford gate is this 3D color code, and it's known to have this transversal T. So if you apply T on the 15 qubits, it's effectively apply a T inverse on the logical qubits. So if you are the researcher at the time, you might say, OK, can I try to understand this code better and see if I can generalize into other contexts? But it turns out color code the construction is quite intricate. And so it might be a bit difficult to just understand the core idea. But luckily, it's later realized that 3D color code is effectively like 3 copies of 3 Tor code. And we understand Tor code much better. And so hopefully, we can extract some idea by just converting the language to the Tor code language. And so for example, since color code has these non-Clifford gates, that also suggests that 3D Tor code should also have these non-Clifford gates. And indeed, it's discussed in the paper, but it's also realized more explicitly in these later works. In fact, we can see a pattern here. So by going to higher dimensional Tor code, that allows us to access higher Clifford hierarchy, like transversal gate and higher Clifford hierarchy. And so later, we'll also try to explain this pattern. But before doing that, let me just try to iterate again what we mean by this 3D color code having this transversal CZ. So here there are 3 surface code. So each of them has encodes 1 qubits. And their X logical operator are these planes and aligned in different directions. So what's known is that you can bring these codes together and apply some local ZZ in parallel. So you take 3 qubits from each layer and then apply ZZ, and you do this in many of these triples. So what's known is that this effectively applies a CZ on the 3 logical qubits. OK, so I hope that's clear. But now the question is, so why do they have such a property? So the claim is that this property really originates from this non-trivial triple intersection number. And so let me explain what this triple intersection number means. So if you take two lines in 2D, they'll intersect at some number of points. And so if you count the number of points, this is known as this intersection number. Well, in 3D, if you take these 2D planes, they will intersect on some lines. But if you take another plane, then now they will intersect at some number of points, and you can count them again. And so that's the triple intersection number. And if you actually think about it, you realize that this is really like a geometric version of the expression that we saw before. So the expression, if we rephrase it, it's the same as like counting the number of coordinates I, such that xi, y, zi are all equal to 1. And so this is really like counting the intersection, because intersection is like the place where like all three planes are present. Okay, so they're really quite similar. And let me point out one more thing. So if you look at the picture of these planes, these three planes really comes from the three logical operators of the surface code. And you can see that they intersect at one point, and which is non-trivial. Yeah, so the claim is that this non-trivialness is why these CZZ has why these surface code has transversal gates. Okay. But you might wonder, okay, why people make such a big deal about these intersection number? Another reason is that these intersection number is a topological invariant. So we know that these logical operators, they generally have like different representations. For example, this blue curve, as long as it's any line coming from left boundary to the right boundary, like all of them represent the same logical operator. Okay, so like all these different representations. And you can see that here, like all of them have the same number of intersection number, mod 2. Okay, and the same property also works in 3D. So here they're again the same three planes, but you can wiggle them, and again the intersection number is again the same. Okay, and we can really relate this topological invariance and the transversality. Okay, so just to summarize everything I've said, the key lesson is that triple intersection gives you a way to build transversal CZ gates on the code, and in fact, you can also generalize some of these into the T gates. Okay, and this also gives you this intersection number also explains the pattern that we saw previously. So in 2D, if you consider this intersection number, that actually gives you CZ gates. In 3D, if you consider triple intersection, that gives you CCZ gates. And in 4D, by intersecting 4 of these like 3-dimensional objects, that gives you the CCCZ gates. And so this pattern continues. And so, yeah, so in fact, this intersection number can also allows you to access like higher Clifford gates if someday we want to use them. In fact, this method is quite general. So these intersection number or cup products, they're indeed utilized in all the paper that Louis have discussed previously. Okay, so now we know that triple intersection is important. So what's next? Well, it's time to build codes with better parameters. So here's a sort of a Venn diagram. So at the center, it's the vanilla Tor code that's built on a torus or realized as surface code. But it's known that if you realize them on the manifold or cellular complex, you can often get better code parameters. So what's the cellular complex? If you look at like one of the picture up there, it's a bunch of squares, and it's glued along the edges. Okay, that's one of them. And on the side, you can see another picture, which is a bunch of cubes and glued along these faces. So that's generally how a cellular complex looks like. And you might ask, OK, what's good about this family? Well, what's nice is that this family, they're often complex enough that you can, yeah, they're complex enough that they often give you good code parameters. But at the same time, they're simple enough that you can actually analyze them. And for example, the recent good quantum LDPC code by like Panteleev and Kalachev, like those codes can be thought of as some code realized in this 2-dimensional simplicial complex. And our code with Louis can be thought of as some realization on this 3D cellular complex. Okay. In fact, in another paper, we also have a very general construction of this family. And this only relies on the local code to satisfy this triorthogonal condition. Yeah, and this is the second step that we talked about, so this local to global kind of relation. So I hope to explain some of the basic ideas about this results, but it seems like we don't have much time, so let me just say a few words on it. So the key idea here is really that the logical operators in these codes, they're really geometrical. Okay, so they're either strings or surfaces. So really, because they're geometrical, you can again define the intersection number. And yeah, so what you realize is that you again want to, okay, so because of the branching structure that we see here, some of these structures, the intersection number is no longer an invariant as before. You have to choose your local codes carefully. And turns out these triorthogonal condition, they allows you to restore these invariants, these topological invariants of the intersection number. And that's why, yeah, that's where this local condition comes in. Okay, and so by combining with the algebraic methods Louis talked about, we can arrive at this final main result. Okay, so let me just conclude. So yeah, so we've constructed codes in 2 of these regimes. So in one of them, we get linear dimension, linear distance, but with large check weights. For the second code, we get codes with low check weights and almost linear dimension, but with polynomial distance. So these code parameters lead to constant overhead magic state distillation or for the first code and near constant overhead for the second code. Okay, so some future directions. So the first one is about improving the parameter for these good quantum LDPC codes. So even though our code has overhead approaching 0, all these code parameters has room for improvements. And the second one is about working with T-gates. So even though CZZ, using the CZZ gates, it can achieve this universal computation. But for some algorithms, it's good to have these T-gates or other higher Clifford gates, which leads to like more efficient circuit implementation. And lastly, because our quantum LDPC code has these transversal CZZ, one might wonder if it's possible to consider a different fault tolerant scheme which directly act on these logical qubits through these transversal gates, so without using magic state distillation. Okay, so that's everything, and we are happy to take questions.
Time for questions to all speakers.
Hi, so thanks for the very nice talk. I have a question about this very nice topological picture that you showed at the end for getting transversal CCZ. So first of all, what about the mod 2? So you said it had to do with there being one intersection point, but that was up to mod 2. So what about if there's 3 intersection points? Does this also give you a CCZ, or?
Because in coding theory, we often work over F2. So everything is already naturally mod 2. So 1 and 3 are really the same in this context.
Okay, thanks. And then one more quick question. So you mentioned as one of the open problems trying to get transversal T. Mm-hmm. And I was curious about, I mean, does this have you tried this construction for T or other things like CS? Is it possible that it applies to that?
Yeah, no, so T's kind of weird because you can get this, like the original triorthogonality work was transversal T up to a Clifford correction. And the natural classical property for that is multiplication over the binary field. But if you want to have just transversal T without the Clifford correction, I think the natural classical property isn't multiplication, it's divisibility. And these methods don't seem to work very well for that. So Yeah, you can convert CCZ distillation to tea distillation just by normal like state conversions, but to directly distill tea, I think yeah, we've tried some things, but it's different ideas. It's further work.
Thanks for the nice talk. You motivated at the very beginning of your talk, of course, all of this by talking about the Easton-Canel theorem. And I'm curious about like what you all think about how we should think of Easton-Canel in light of these nice results. Like, was it just, you know, were its assumptions too restrictive, or is it still fundamentally an issue? And there's some other place it will show up if I try to use these codes, that sort of thing.
Okay, I'll go ahead. So indeed, as you pointed out, like the Easton-Canel only require on-site sort of these operations. But indeed, in fact, for fault-tolerant applications, often finite depth is also it's a weakening of this condition, and now it's unclear whether like you can go around the Easton-Canel theorem essentially. But on the other hand, while studying these topological features, it also seems like these CZZ, they're naturally three-dimensional. There's some kind of sense of three-dimensionality going on. And the H-gate, for example, there seems that it often requires like the X logical and Z logical to be dual to each other. So there seems to be also some dimensional mismatch going on. So let me be a bit more precise. So in the 3D code, the X logical operator are often like two-dimensional, but the Z logical operator are one-dimensional. And so it seems like it's impossible to get H-gate because you have to convert between two-dimensional and one-dimensional objects. So there seems to be some barrier, but I don't think I have a proof. Yeah.
Yeah, can I just add to that? The Easton-Canel theorem is a bona fide mathematical proof. What's going on here is that we have an outer code which supports Clifford transversals, and then effectively you're inside that, like you're concatenating with a code that supports non-Clifford transversals. So you can, yeah, that's what's going on. So there's definitely no one code that supports a universal set of gates, but yeah, what's going on here is you have non-Clifford inside of Clifford.
One quick final question, please.
Hi, thank you for the very nice talk. I wanted to ask about the distinction between the gamma going to 0 and gamma exactly equal to 0. So Adam mentioned that to get gamma exactly 0, you have to really go beyond this Bravi-Ha kind of paradigm of magic state distillation. Is it known kind of like general conditions for which codes actually support gamma exactly 0 versus just going asymptotically to 0?
So, so for now, what we think, the code that we think is required to get gamma equals 0 is asymptotically good. So you need K scaling with N and also D. And the reason is because the Bravi-Ha protocol is a concatenation protocol. So you will naturally you will naturally not get non-constant, will not get constant overhead with this concatenation. But with this good code, you can just do one round of distillation. And then the constant overhead just follows from the constant rate of the quantum code.
Oh, I might add, I think especially having constant rate is very important.
Right.
Yeah. Distance might be negotiable.
Oh, that's right. Yeah, distance, you only need to be able to error correct random errors over the...
This also just gives me an opportunity to say one thing that I wanted to and forgot, which was that the scheme itself, like using error correction, that has very much been done in distillation before. That idea is not super original, but like what's original is having the code and then doing the analysis to show that you can get the constant overhead, constant threshold.
All right, let's thank the speakers again. Before lunch break, we have an important announcement, but please connect to the speakers for the rest of the conference, for the rest of the questions that you have.
Good morning, all. Just want a brief housekeeping. This room, Ballroom AB, will be closed until dinner. Please take all your belongings with you. Our afternoon parallels will be in 402, 301 AB, and 302 BC downstairs. Today, for dinner, specific dietary cards will be on the ballroom lobby for collection during the poster session. Many attendees requesting dietary accommodations will not need to pick up a card. Student volunteers will be on hand if there are questions. And those with dinner guests, please collect a badge for them before 5 p.m. today at registration. Lastly, the registration desk has posters from yesterday's session if you need to pick them up, as well as lost and found items, a pair of glasses, a water bottle, a travel coffee mug, and an HP charger. And lunch is available in the cafe on the 300 level today. Thank you all. See you at dinner.